Hello! In this video, we are going to derive these formulas for curvature when it comes to TNB frames. Now, if you recall, curvature is defined as the magnitude of the derivative of the unit tangent vector with respect to arc length. Now, really, we can re-express dt over ds as dt over d time over ds over d time. Right? Really, going from here to here, we're just using an idea from parametric equations. If you recall, from parametric equations, this is another way that we can express dy over dx. And so we're performing a similar thing that we did here. Now, next, I'm going to re-express ds over dt in a different way. Now, really, ds over dt is the derivative of arc length with respect to time. Okay, so then how is arc length related to time? Well, if you recall, arc length is related to time by the following formula. And if we take the derivative of arc length with respect to time, really, to take the derivative of this with respect to time, we just have to use the fundamental theorem of calculus, which is to say we take the integrand, and all we do is we replace u with t. Right, and so this is s prime of t, which is the same thing as ds over dt. So really, ds over dt is equal to magnitude of r prime of t. But in a shorthand way, I like to write magnitude of r prime, because when we see a prime, we're assuming that that's just a derivative with respect to time. So yeah, we're going to replace ds over dt with magnitude of r prime. Now, I'm actually going to rewrite this in a slightly different fashion. Now, really, notice that this is the magnitude of a scalar times a vector. So really, this is in the form of magnitude of kV. But if you recall, whenever we have something in this form, what we can do is we can pull the scalar outside of the magnitude. But when we do that, we have to make sure that we put an absolute value in front of the scalar. So really, we're going to apply this property to what we have here. We're going to pull out the 1 over magnitude of r prime from the magnitude and put an absolute value in front of it. And so this is what we really get. Now, I'm actually going to move over here, and notice 1 over magnitude of r prime clearly isn't negative. So really, we don't need the absolute values in front of it. Now really, we can rewrite dt over dt as t prime, right? That's our shorthand notation for derivative with respect to time. And so now we can rewrite this as magnitude of t prime over magnitude of r prime. And so this completes the derivation of our first formula for curvature. So now we're going to show that curvature is equal to this thing, which is a little bit more complicated. And there's a couple ways that we can derive this, but what we're going to do is we're going to compute r prime, then compute r prime prime, then we'll take their cross product, and then take the magnitude of that cross product. And we're going to see if we can bring this guy into the picture. So let's start by computing r prime. Now, what do I mean by compute? Well, really, I'm going to write r prime using the unit tangent vector. If you recall, the definition of the unit tangent vector is this. Now, I can multiply magnitude of r prime on both sides so that I get r prime is equal to magnitude of r prime times the unit tangent vector. Now, as we showed earlier, the magnitude of r prime is really ds over dt. But for convenience, I'm actually going to use our shorthand notation for derivative with respect to time. I'm going to rewrite ds over dt as s prime. Right, so this right here is r prime. Now we're going to compute r prime prime. Now to compute r prime prime, we have to take the derivative of this thing with respect to time. Okay, so taking the derivative of this thing, we see that the derivative of r prime is just r prime prime. And to take the derivative of this thing, we're going to have to use the product rule. So if you recall, the product rule basically goes like derivative, no derivative, plus no derivative, derivative. So really, if we use the product rule, we will get this. And so this right here is r prime prime. So we've computed r prime, we've computed r prime prime. Now we're going to take the cross product of r prime with r prime prime. But really, that means we're doing this vector crossed with this vector. Because really, it's just r prime cross r prime prime. And so notice we're taking the cross product of something in the form a cross b plus c. But if you recall, the cross product is distributive over addition. So really, this is just going to be a cross b plus a cross c. And so applying this rule to what we have here, we get this. Now notice in this first cross product, we have two vectors that are both parallel to the unit tangent vector. Well, really, that means that these vectors are parallel to each other. But if we take the cross product of two vectors that are parallel to each other, then their cross product is 0. So we know that this first product, or cross product, is 0. So really, r prime cross r prime prime is just equal to this. But if you recall, another rule for the cross product is that we can pull out the scalars from it to the front. So really we have s prime times s prime, which is s prime squared. And then we're left with t cross t prime. Now what we're going to do is we are going to re-express t prime in terms of the unit normal vector. Turns out it's going to be useful if we do that. Now, if you recall, the unit normal vector is given by this definition. Therefore, if we multiply magnitude of t prime on both sides, we get that t prime is magnitude of t prime times the unit normal vector. And so really, we're going to replace this t prime with magnitude of t prime times the unit normal vector. And so again, we can pull this magnitude of t prime out to the front. And so if we do that, we get this. But if you recall, the unit tangent vector crossed with the unit normal vector is the unit binormal vector. And so this is what we have. Now notice that this cross product is really just this positive scalar times the unit binormal vector. Well, the unit binormal vector has a magnitude of 1, which means that the magnitude of this cross product must equal what we have in front of the unit binormal vector. Now, let me go back to re-expressing s prime as magnitude of r prime, right? If you recall, s prime is equal to magnitude of r prime. And what we're going to do from here is we're going to go back to the other formula that we now have for curvature, which is curvature equals magnitude of t prime divided by magnitude of r prime. But now I think it's pretty clear to see if we multiply magnitude of r prime on both sides, we get that magnitude of t prime is equal to magnitude of r prime times the curvature. And so really, we're going to replace this magnitude of t prime with magnitude of r prime times the curvature. And so this is what we get, and therefore, dividing this magnitude of r prime cubed to the other side, we get the exact thing that we have here. And so this completes the derivation of the other formula for curvature. And so yeah, that's pretty much one way that we could go about deriving both of these formulas for curvature. And so yeah, that's pretty much the idea of how it works. So yeah, that's pretty much it for this video.